So now we're going to move on to model tuning to see if we can get a better model by tweaking some of these different model parameters. Now, we are not going to be working with any other models other than logistic regression in this mini course. And that's because I think this is something that would be interesting for you to play around with because scikit-learn makes it very easy to use a bunch of different other models the exact same way that you use logistic regression. So for example, if we were to say, from sklearn dot under the ensemble submodule here, we can import, for example, random forest classifier. And this random forest classifier, we would do the exact same thing that we did with logistic regression. So we would instantiate it like this. We would, get our accuracies by passing it to cross-val score with our X train and our Y train data, and CV equals 5, and scoring equals accuracy. We could look at the mean of those accuracies, and we see, okay, we're getting like 94, 95%. It's the exact same basic format as logistic regression, but obviously this is a totally different underlying model here. And so we're going to stick to logistic regression for right now, but I encourage you to check out what other models are available. And so, if we just Google scikit-learn, classification models, let's just see what this comes up with. So this one is by this other website, but let's just go into scikit-learn. Supervised learning, in case you're less familiar with the term, means we have the labels. So this is an example of supervised learning. We know what the answer should be. We know what the species of flower should be. That's what logistic regression is, and it's what a lot of these other things are. So you can check out all these different models, and I would encourage you to play with some of the classification ones. And that's something that you can do kind of on your own time. So we'll stick with logistic regression for right now. I'll go ahead and delete all these. And we're going to do model tuning. And now, so what is model tuning? What is model tuning? So model tuning is trying to determine the parameters of your model, and these are also known as hyperparameters. Trying to determine the parameters of your model that maximize the model performance. So in this case, remember that we set model equal to logistic regression, and other than our max iterations of 200, we left all of the other parameters as the defaults. So the question is, can we change some of those model parameters and end up getting better results out of our model here? So let's take a look again at what parameters we have to play with. So you might not be familiar with what a lot of these are, but I'm going to point you to one, which is one of the most important, and that is this C parameter here. Now, this is regularization, and regularization is going to be one of the more important parameters, one of the more important aspects of any machine learning model, any data science model, kind of any statistical model, is this regularization. And so with any kind of model that you're dealing with, it might go by different names, but the underlying concept is regularization. And we're not going to go too into depth into this right now. I definitely encourage you to learn more about this, but essentially what this means is how much flexibility do we give our model to fit all of the different data points, even if that means we might start overfitting. And if you remember, that overfitting kind of means memorizing data points. So if we give it a lot of flexibility, then we say, it's okay if you lean a little bit more towards the side of memorization. if that gives you maybe a slightly more powerful model to learn more of the complexity of the data. And if we go the other way, if we regularize it more, then we're saying, we actually want the model to be simpler, even if it means it's not learning quite as much about the patterns of the data, but that also means that it's not quite as prone to accidentally just memorize the different data points. So in this case, let's play around with this value of C here. So let's see, what does it? Inverse of regularization strength. So smaller values specify stronger regularization. So smaller values mean simpler models, mean smaller values means we don't want it to accidentally memorize data points. Bigger values means that we're slightly more okay if it goes in that direction. So let's play around with this value for C. So maybe we try, so C equals 1 was the default. What if we try C equals 0.1? Let's see what happens then. So we'll do model equals that. And we'll do our cross val score with our model, our X train, our Y train. Let's do CV equals 5, and we'll say scoring equals accuracy. We'll say accuracies equals this. And let's go ahead and let me go find that nice printing formatting that we used earlier. Here we go. So we'll print the np.mean of the accuracies times 100, and then we'll format it with 2 decimal places. And let's change this to be accuracy. All right, so here we get 94.6%, which I believe this is actually lower. I believe this is lower than before when we had a model with a value of C as 1. So actually, let's copy this into this cell. And we can just try different things. So we try C equals 0.1, try C equals 1. Yeah, so this gives us an accuracy of 97%. Let's try C equals like 5. Well, that actually gives us kind of the same accuracy there. So C equals 10. So it looks like in this case, due to the structure of our data and our logistic regression model can't, just due to the nature of the model, it can't get that complex. It can't memorize the data too much, and we only have 4 input features here. So even if we allow it, even if we don't regularize it very much, which increasing the value of C means we're not regularizing or penalizing this this model, it looks like we still get about the same. Oh, well, there we go. If we increase C by quite a lot, then it drops the accuracy down. So maybe if we increase our max iter again. Okay, so we're finding some spaces here where our accuracy is not nearly as good. So let's go back to down to 200 and back to C equals 1. Now, what if we play with some values right around C equals 1 where our accuracies were changing? So maybe what we want to do is, let's say for reg param, so regularization parameter, let's try a few different things here. Let's try 0.1, 0.3, 0.9, 1, maybe 1.3, 1.9. Let's maybe try these. So we'll print reg param, and then we will train a model with that regularization parameter, and then we will print the accuracy. And this is pretty interesting, actually. If you notice that with very small values for C, our accuracy does suffer. And then it goes up to about 97%, which is what we had before with c equals 1. And then we do actually get a little bit better accuracy with a slightly higher regularization value here. So let's keep going. And maybe let's just start at 1. And we'll do 1.3, and we'll do 2. Maybe we'll do 5. Maybe we'll do 10 and 100. Let's see what happens here. So it looks like our best accuracy so far is for c equals 2. So what if we try some values right around there? So let's try 1.8. We'll try 2.3. We'll try 2.9. We'll try 3. Let's see what happens. And it looks like we max out here right about 98.2% for a C value of 1.8 or greater, or 2 or greater. So this is kind of what model tuning is it's taking these different parameters for our model that we have access to, trying different values, and there are more intelligent ways to do this, by the way, than just kind of randomly guessing. One of them, for example, is Bayesian hyperparameter optimization, which is definitely one of the main go-tos these days. If you're actually going to, once you understand what you're doing here, I would definitely recommend using something like Bayesian hyperparameter optimization. But to start with, I think that manually trying things is a really good way to learn like this. So we just tuned our model, and maybe we say that our final model is, maybe we want a max iter of 200, and we want a C of 2. And this is a good final model here. All right, so now we're on to the last part of what we're going to be doing here, which is pretty exciting. So we have our final model, and now, actually, I'm going to create a new section, which is just going to say final model. And now is the time that we see how well our model does on the test set. Now remember, this is the completely unseen data that we set aside from the very beginning, before we started doing any of this modeling. And so this is really what we care about, is how well does our model do on quote unquote new data from the world. Because we're going to want to use this to predict species of new flowers, or some other kind of thing. Like, we're going to have real data coming in, and we're going to want to make predictions about it. We're going to want to understand it. So how well does our model do on the test set? So let's go ahead and see how this does. So the first thing that we're going to want to do is, let me jump back up to the top here really quickly. And we split out our X train and our Y train data, I believe. Yep, X train and Y train, but let's see. We did not split out the test. So I'm going to copy this. Let's copy this down here. And we'll say X test equals df test dot drop columns, target name, etc. And Y test equals df test. Now if you look at X test dot shape, so remember we set aside 38 values to evaluate our model on. Now, and these are the real species. So these are the actual species of the flowers, and we're going to see how well our model predicts these. So the first thing that we do after we split out our data is train our final model using our full training data set. So now that we're done picking our model, and now that we're going to be evaluating it on this unseen data, we can use our full training data set to train the model one last time before evaluating it. So we'll do model.fit, xtrain, ytrain. There we go. So we fit it, our C equals 2, our max iter equals 200. All of these other model parameters are just the defaults. And now let's go ahead and just get our predictions. So we'll say y test pred equals model dot predict x test. So we pass in our x data. We're making predictions of what the species is going to be. All right. So kind of the moment of truth here. Let's say our test set accuracy, and this is going to be y test pred equals y test. So this is going to be, did we classify it correctly? And then we say, so this is test set correctly classified. And then we can say test set accuracy equals np.mean test set correctly classified. And now let's do test set accuracy. And remember, we'll do the times 100 to make it into percent. And then we'll format it to 2 decimal places. All right, so here we go. So our test set accuracy, 94.74%. So this is pretty good. If you remember that our final accuracy here on our training data was 98%. And so our test set accuracy being a little lower, this might show that we are slightly overfit on our training data because we're not doing quite as well on unseen data as we did on the training data. And this is a very natural kind of process to go through and to say, okay, we did maybe a little bit better as we were training and not quite as well on new data, but still very well. So let's see which points we classified correctly and which points we classified incorrectly. So first things first, we're going to want to create our predictions data set just like we had earlier. So I'm just going to take a look really quick at our test set correctly classified. Yep, got some trues, got some falses. Oh, and it looks like we only actually missed 2 points here. So, this is one of the things about your data set being so small is that, 2 points being missed can lead to a couple point drop in accuracy here. So this is still doing very well. So let me scroll back up to where we created our predictions data frame. And I am going to, I'm going to copy these down to the bottom so we can create a data frame for our test data set here. So let's copy this down, use X to delete that, scroll down. All right, so we'll say df predictions test equals df test.copy. And then we'll change all these to be df predictions test. And df predictions test there. The scroll bar kind of gets in the way. All right, so y pred, so this is going to be y test pred now. And we could create a function to do this as well. And test set correctly classified, we'll set that equals to that. And now if we create this df predictions test dot head, there we go. So here's an example of one of the data points that we got wrong. So we predicted Virginica and we got versicolor instead. So now that we have this data frame, we can use our plot incorrect predictions function with this. And remember that we have our x-axis feature. We'll keep that as petal length. And we have our y-axis feature, and we'll keep that as petal width. And here are our 2 points that were misclassified. So if you notice, it looks like we predicted both of them as Virginica, and they were both actually versicolor. And this is, once again, kind of right on that cusp there. So right in that region where it's hard to differentiate one thing from another. And you can see that it is, it's very reasonable to think that these 2 data points from these 2 features that would fall into the orange Virginica class here rather than the blue versicolor. But our model is doing very well overall. It's predicting most of these points correctly, and that is super cool.